Welcome to Dr. Jed's continuing calculus video series. This section is section 4.7 from Rogowski, which is on optimization. Actually, optimization with a subtitle, Story Problems. They're best handled through examples, but the examples are long. We'll do two. Hopefully that will be enough to give you a feeling for how to do these. First, we'll go over the steps of what you should do. Then we'll do the examples, and you'll see what we can do. So to solve these, the first thing to do to optimize some function. Optimization, by the way, means finding an absolute min or an absolute max. The first step would be to read the problem statement. It's always going to be some kind of word problem. And to understand what's going on in there. That doesn't mean you solved it. It means you know what they're asking. Then, typically, you draw a picture. This is not always necessary, but it's often helpful. Label every quantity you can. Sometimes you don't know what the value is. Often you don't know what the value is. But you still label it. Label it maybe an X or a Y or something else. Then, and this is also important, you need to identify what it is you're trying to optimize. What's supposed to be maximized? What's supposed to be minimized? It's important because that's the formula that you're going to be using. That's the function you're going to be using. Then, we take that function. Often it's in more than one variable. It's critical it gets down to one variable. This is a one-variable calculus course. And if it's got an x and a y and a z in there, we can't maximize with three variables. So we figure out what y and z are in terms of x, replace it all in, and we get a function of one variable. Then what? Well, we optimize it. What is that to say? We want to find where its max is or where its min is. How do you do that? We apply calculus. What does that mean? We take the derivative, we find the critical points, we find the endpoints, we plug them all in. This was from a long time ago, and it's just application of that method. Now, if the endpoints don't exist, we have to worry about it. How do you figure it out with no obvious endpoints? Well, once you have the answer, that's not necessarily the answer for the question. The question might have asked something else. So you need to figure out what they asked and answer it. Got it all? Let's try it. A farmer has 1,600 feet of fencing to make two rectangular pens that share one side. What dimensions maximize the area of each pen? Well, the first thing we need to do is figure out what's going on. So think about this, see if it makes some sense, see if you can understand the question. Then we're going to go on. So let's go on. We're going to draw a picture. Two rectangular pens that share one side. Hopefully. This is what you were thinking of. Now, it says, what are the dimensions of each pen? Presumably, in this case, the pens are the same size. If not, then we have to worry about which pen and what. But that's a simplifying assumption we can use, or we could not, and just talk about the top here and the bottom here as being sides. But in any case, we have to identify variables for each of these. I'm calling all of those x. Why? Because if this is x, that better be. I'm going to make the assumption they're the same size as a pen. Is this also x? Maybe. But we know they're rectangles. So this we'll call y. We'll call that y. We'll call that y. Now what is it we're trying to maximize? Maximize the area of each pen. So there's a pen. What's the area of it? The area is what we're trying to maximize. And just like I had said, sometimes that has more than one variable. There are two variables here. So we're going to have to figure out what to do to reduce that to one variable. Hopefully there's more information that we've overlooked. And if you look back, there is. There's 1,600 feet of fencing. How does that play into all of this? Well, there's all the fencing. How much fencing is there? X and X and X and X. So 4 X's. And 3 y's, that's 1,600 feet of fencing. So if I want to get rid of y, I can solve for y here. Bring that over, divide, I get y equals minus 4/3 x plus 1,600 over 3. That's what y is. I can plug that into here. Minus 4/3 x plus 1,600 over 3. Now, I could leave it like that, but it's not a very pretty way to do it, so I'm going to multiply through. So I have the area in terms of x is minus 4/3 x squared plus 1600 thirds x. There's our function we need to optimize, which means we need to maximize it or minimize it. In this case, maximize. Well, we're actually almost done. What do we do next? We find the critical points, which means we take the derivative. And we set that to 0 or doesn't exist. And doesn't exist, oops, there's no x there. Doesn't exist is not going to have any answers, but in fact, there is an answer for equals 0. You can do a little bit of work here. You get x equals 200. Now, I'm going to run out of room, so I'm going to go to another board, but I want to bear in mind a couple things. That is our critical point. It's not necessarily our answer, but it might be. Well, it might be an answer, but not an answer necessarily to the question. We also need the endpoints. How big could x be? Well, look, we could shrink this down, make the y's really tiny, but there are still 4 x's. So the biggest x could be, it's going to be 1/4 of that. Likewise, the smallest x could be. X is a positive quantity, it's a side. But if you shrink it down to the smallest it could be, you could get 0. So here are the 3 places we're going to test for this function. And then as I move to the other board, there's one other thing I want to know. What are we going to ask? What dimensions are we looking for? When we get to the answer to this, that's what we'll get. So, rewriting, the function is that. The tested values are those. Put a 0 in. It's actually easy to do. Put a 400. It's harder to do. But actually, it's not as hard as you might think. Because 400 times 4 is 1600. Times the other 400, there's the other 400 there. This is also 0. This is the one that's trickiest. And if I plug that in, I get 2 times 2 is 4, times 4 is 16, minus 16, but over there is 32. It looks like I get 160000 over 3. But it doesn't matter. These are the endpoints. That's the critical point. We're trying to maximize this. Which is the maximum? Right here. That would be the answer if that's what we were asked for. But we weren't asked for that. We were asked for the dimensions. So, well, the x is 200. But there's another dimension, y. And if you think back, we know what y is. Think back. It was minus 4/3 x plus 1600 over 3, which is 800 thirds. There is our answer. That's the maximum. Now, let's try a slightly, perhaps easier one to visualize. Maybe even more abstract, but different kind of category. The production of a light bulb factory. I got this from the book, actually. Is P equals 2Lk squared in millions. That's the millions of productions. Where L is labor cost, K is the equipment cost in the appropriate units of money. What's the minimum total cost to produce 1.7 million units? There's no picture. But there is a formula. What are we trying to maximize or minimize? We're trying to maximize or minimize total cost. The total cost would be the labor cost plus the equipment cost. So our function, cost, is L plus K. We want to minimize that. What else do we want to know? Well, we want to figure out, that has 2 variables. That's no good. But we also know P equals 1.7. So P, which is 2Lk squared, is 1.7. Now that's not a very pretty thing, but we can solve for L. I do that, divide, divide, I get L is 1.7 over 2k squared. Why am I doing that? I need to have one variable in order to maximize. I now have a function of one variable, and I want to minimize this. Well, I take the derivative. Quotient rule. Well, actually, or you could just use the rule power of, this is 1.7 over 2 times k to the minus 2. So, I get that. I actually have two critical points. One is when k is 0. And the other, if you set that to 0, solve it, you get the cube root of 1.7. Now, these are critical points, but are they in the region? What's the smallest k could be? Well, possibly 0, but if k is 0, we're going to have 0 production, and we don't want 0 production. So this is a false answer. How big could k be? Well, there is no limit, because L could be as small as you want. So the limit for k, the endpoints, zero doesn't work. And the biggest k, you could have lots and lots of equipment and almost no labor. That's not also going to work. Why? Because that's a lot of money you're spending without getting the results you want. We actually have no choices in this matter. This is a function that, if you look at the derivative, as k is small, we have a function that is, well, if k is small, this is big. We have a negative. If k is big, that's not very big. It'll do that. By looking at the derivative, we can see the endpoints don't even matter. Why? Because that's got to be the smallest. Now, is that the question we had? What is the minimum total cost? So that's not the question we had. We want to know the total cost, which is this. So the answer to the question is k plus 1.7 over 2 k squared. That can simplify, because this is actually 1.7 cube root of cubed. Cancel them out, and you get 3/2 of the cube root of 1.7. A decimal answer is probably more satisfying, but algebraically that is the right answer. This was only 2 examples out of many, many, many kinds. Hopefully, though, it at least whets your appetite for trying some out.